Last time this slide, move on. Okay.
Okay. Hey, thank you for your patience. So we'll have Lino, who is actually now also acting manager of the fab, will present you.
Okay.
Okay, Lino.
Thank you, David. So, hello everybody, my name is Lino Eugene, and I work at the McGill nanotech microfab, and today I will present to you an introduction to microfabrication. First, I will tell you about the history and the evolution of microfabrication. Then I will talk about the basic steps of microfabrication, and I will show you the example of the SEM master for PDMS molding. And finally, we will talk about our facilities, the McGill nanotech microfab. So the microfabrication techniques originate from microelectronics. And here is a brief history of microelectronics. So in 1947, 3 researchers from Bell Lab created the first transistor. In 1958, Texas Instruments fabricated the first integrated circuit. And 3 years later, the first integrated circuit in silicon was made. In 1971, Intel commercialized the first microprocessor with 2,300 transistors inside. Today, you can find transistors, microprocessors with more than 2 billion transistors inside. This huge evolution is possible thanks to the development of microfabrication methods for over 40 years. Some of them are dedicated to microelectronics, but most of them are used in different microtechnology subfields. So I would like to know how many of you have a smartphone or tablet. A lot of people, of course. Okay. So can you tell me which components are inside this kind of device? I'm pretty sure you know it's not it's very easy. You know some of them. So they, yes.
A processor. There's an accelerometer. There's optical sensors for light. There's a camera.
Right.
Sometimes 2 cameras. Sometimes 3.
Yeah. So microprocessor for calculation. Microprocessor for graphics. So you need a CCD, so charge coupled device, to take pictures. You have a light emitting diode for light, and you have also microphones. Okay, so let me take a picture of you. Okay, so you will see, do you see the white light? So it's come from the light emitting diode, okay? So if I look at this picture, okay, so a nice picture of you. When I rotate the phone, you can see there is auto rotation of the image, and this is possible thanks to micro accelerometers and gyroscopes. Okay, you will find these devices, this component also in the controllers for Wii and PlayStation 3. Okay, and even in hair dryers. My girlfriend bought hair dryers with a sensor. When you put on the table, it stopped to run. Yeah. Okay, so you can see in today in consumer electronics we have a lot of components fabricated from this. The 3 first microtechnology subfields. So, oh, sorry. Oh. So microelectronics, optoelectronics, and micromechanical systems. Microstructures and nanostructures can be very useful also in microbiotechnology. They can be used for to analyze DNA or to analyze fluids like blood. So microfluidic systems are used a lot to analyze this kind of biological structures. Today, nanotechnology has evolved into nanotechnology. So in nanoelectronics, many researchers try to replace the standard silicon channel of transistors by nanostructures like nanowires, nanocrystal, nanotube for logic and memory application. In these nanostructures, quantum effects can also appear, and they can be used to build a quantum computer. In nano-electromechanical systems, so you can fabricate tips for atomic force microscope. Carbon nanotubes can be used as axes for nanomolecules. You can see this small video here. And they can be used also for sensor to sense gases, for example. In nanobiotechnology, there is a huge work in using nanoparticles as a delivery system to cure locally disease like cancer. They can also be used as sensors to detect cells affected by viruses. So to fabricate this nanostructure and micro nanostructures, we need a controlled environment. So why controlled environment? So first we need to reduce the number of particles because dust particles are very large compared to micro nanostructure and they can destroy these structures. Okay? And any fluctuation of humidity, temperature, or vibration can affect the photolithography process to define new patterns. So it's very critical. How it's possible? So in clean rooms, air continuously circulates and is filtered. Positive pressure is applied to keep particles outside the clean room. The users have to wear clean room suits. So these suits consist in hood, safety glasses, coverall, gloves, and boots. Liquids and gases and chemicals have to be highly purified also because they will be in contact with wafers or silicon wafer and other semiconductor substrates. And special furnitures are also needed inside to prevent any particle spreading inside the clean room. So clean rooms are classified on the basis of particle counts per volume. So we use the class number, and the class number corresponds to the number of particles larger than 0.5 micron in 1 cubic foot. In semiconductor industry, like Intel, clean rooms have a class 1 to 100. In a surgery room, the class varies between 100 and 10,000. And in a house, the number of particles can reach 300,000 particles. So you can see that clean room in semiconductor industry are cleaner than surgery room in hospital. And also, if you want to stop cleaning your house, you have to live in clean room, but it will be very expensive for you. Okay? And so now the wafers. So the wafers provide mechanical support to your micro and nanostructures. They provide also specific electronic properties according to the application you need. So the silicon is the most widely used in the semiconductor industry. Silicon is the second most abundant element in the Earth's crust after oxygen. Can you tell me which raw material is used to get silicon? Je think, sorry?
Sand?
Yeah, right. Sand. So sand is used, sand from beaches are used to fabricate silicon. And I think that the production, most of production comes from Australia. So this sand has to be purified, of course, because there are a lot of impurities inside. So the sand has to be purified to get an electronic grade silicon. And from this electronic grade silicon, we can grow single crystal ingots. These single crystal ingots are sliced and polished to obtain wafers of various sizes and thicknesses. So the typical diameters of wafers are 2, 4, 6, 8, and 12 inches. Other substrates, other material can be used also depending on the application you need. Quartz, fused silica, and glass wafers are very useful when transparency is needed. They are mainly used for the fabrication of screens and displays. The 3-5 materials are well known for the fabrication of light-emitting diodes, laser diodes, and photodetectors. Silicon carbide and sapphire wafers are typically used for power electronics and also for light-emitting diodes fabrication. And the last one is plastic substrates are very useful when flexibility is needed. So they are used in organic electronics and in the fabrication of flexible displays. So all these materials, except for quartz fused silicon glass, are more expensive than silicon because they have to be synthesized.
No?
Yeah.
See your wafer?
Yeah. I can show, yeah, also good. This is a wafer which comes from Teleda and Dalsa at Beaumont, and you can see arrays of CCD, charge coupled devices for photo detection. So this is a 6-inch wafer. I think that there are maybe more than 100 components on this wafer. So on the wafer, you can deposit, you can use thin film deposition to add more functionality to the wafer, like conduction, transparency, or hard masking. The deposition technique can be divided in 5 categories. The first one is physical vapor deposition. The physical vapor deposition is based on material ejection. The atoms are ejected in a vacuum from a target to the substrate surface. The ejection can be done by various means. Sorry, I think there is a timer. There's a problem. So the ejection can be done by various means: resistive heating, electron beam heating, or ion bombardment. Thanks to physical vapor deposition, elemental metals, refractory metals, their oxide and nitride on alloys can be deposited. So the second category is the chemical vapor deposition. In a reactor, source gases are introduced, and they react and decompose at the wafer surface at high temperature. The decomposition and reaction of these gases can be improved with a plasma at lower temperature. Thanks to CVD, silicon and its compounds can be deposited. The third one is epitaxy. Epitaxy is a special case of thin film deposition. In fact, the crystalline information of the substrate is transmitted to the deposited layer. Okay, and silicon, germanium, and 3-5 materials are typical materials grown by epitaxy. Electrical chemical deposition is a process by which a metallic film is deposited from a solution of ions onto electrically conductive substrate. So this technique is widely used for the fabrication of copper interconnection in the microprocessors. And finally, spin and spray coating are widely used to deposit photoresistant polymer. In the next slide, I will talk about spin coating. So, lithography is used to define patterns on the substrate. There are 3 main steps. The first one is spin coating. So first, few milliliters of resist is dispensed on the wafer surface. Then the wafer starts to spin in an accelerating manner to spread the resist over the whole surface of the substrate. The spin coating typically runs between 1,000 and 5,000 RPM for 30 to 60 seconds to get a uniform layer. And the last step is soft bake, or to drive out most of the solvent from the resist. The main parameters of spin coating are viscosity of the resist, the spin speed, the bake temperature, and duration. The typical thicknesses of typical thicknesses of photoresist are from 10 nanometers to 100 micron.
With this, is it normally thinner at the middle and thicker at the side? Or?
You're right that it's thicker at the edge. It's called edge bead, okay, because of surface tensions. It's thicker at the edge, and sometimes we have edge bead, a process called edge bead removal. So we use a solvent to remove the thicker resist at the edge of the wafer.
So it's just the edge. How much thicker is it, and how wide is that?
It depends. It depends on a lot of parameters. It depends on the viscosity of the resist. It depends on the spin speed. Okay, but it can be twice.
But the middle isn't usually.
No, the middle, no. This is the it depends also on the size. So if you use a wafer, for sure it will be very uniform. But if you use a very small sample, it will be hard. It will be very hard to get a uniform thickness. Yes.
Is this optical lithography or also e-beam lithography as well?
I will talk about e-beam lithography. But this is optical. But for spin coating, you use also e-beam. You can spin coat e-beam lithography resist. At this point, it's the same. They're the same step.
What's the critical sample size to have a uniform layer? Like you said, if it's below a certain size, you won't.
It's very difficult to answer to this question because it depends. I know that some projects you have very expensive substrates, and sometimes students use 3 by 3 millimeter sample, and it's very horrible to manipulate. It's awful. And normally, I think that the minimum size should be 1 by 1 centimeters. Okay. And yeah, for sure, 3 by 3 it will be very difficult to get an uniform layer. And even with the tools we have for photolithography and for vacuum to hold the sample during process, it will be very hard. Yes?
But your 3 by 3 millimeter, couldn't you stick it on another wafer to use it as another substrate?
Yeah, of course. Yeah, you can do that for reactive ion etching, for example, for plasma etching. But for photolithography, it will be very difficult, I think, because you will the pressure will be happen only on this small sample, and I'm not sure it will be uniform. Also.
One solution should be a spray coat, right?
Yeah, I will down to of course, spray coating can be a solution to dispense resists. But I will not talk about this technique. So the second step of photolithography is UV exposure. The source of UV is a mercury lamp with different peaks. Okay, and UV radiation is uniformly distributed over the wafer through a photomask. And here you can see an example of photomask. So a photomask is a glass plate with chromium patterns which block light. And I have 2 examples here. I have a dark field photomask, which means that chromium covers most of the area of the photomask, and this is a transparent field photomask. So the area is, most of the area is transparent. Okay. The main parameters of UV exposure are the resist thickness, the gap between the substrate and the photomask, and the exposure dose or time. We can expect a resolution of about 500 nanometers in the best condition. And best condition means that there is no gap between the substrate and the photomask. Otherwise, you can get the patterns will be deformed by, because of UV diffraction. So these conditions sometimes are very difficult because you have to keep clean the photomask and your wafer. If you have a particle, for sure, it will be very hard to get a good contact. And also for the edge bead, you talk about the edge bead should be removed to get a very good contact. The last and third step of photolithography is development. So we use an alkaline developer, which is typically a diluted TMAH. So TMAH is tetramethyl ammonium hydroxide. And this solution of TMAH etches away the soluble parts of the photoresist. the solubility of the photoresist depends on the polarity. So there are two polarities for the photoresist. The resist can be negative or positive. So on this sketch here, you can see a photomask with a square chromium area. So this area will block UV light. So for a positive resist, the exposed area of the resist will be dissolved in the developer. So you can see only this part will stay after development. Whereas for negative resist, the non-exposed areas of the photoresist will be removed in the developer. Yeah. When high resolution is needed, you can use e-beam lithography or electrolithography. So the resist can be also positive or negative, and the e-beam resist can be spin coated like the photoresist. But we don't need a photomask. This is a maskless process. This is very flexible, and you have only to design your layout in the CAD software. In theory, you can get a resolution below 10 nanometers for e-beam lithography, but the resolution depends on the resist material, the thickness, and the electron energy used. So now let's talk about the etching. So etching is used to transfer the patterns to the underlying layer. Okay, and in etching, we have the wet etching. And the reaction between a solid and liquid etchant results in a soluble products. In general, wet etching is isotropic, which means that the material is etched in all directions, and you can see a typical curved profile of wet etching. But there is one exception. There is exception especially for crystals. And in the next slide, I will talk about wet etching of silicon, crystal silicon. During wet etching, mask undercut can occur also. And due to this mask undercut, it's very difficult to control precisely with small geometries and closely spaced structures. However, the main advantage of wet etching is batch processing, which means that you can process 25 wafers at one time in industry. So this is a special case of wet etching of silicon. When we use a base etchant like potassium hydroxide or tetramethyl ammonium hydroxide, the etch rate in 100 crystal planes is higher than in 111 planes. So anisotropic wet etching of silicon results in V-groove geometries. And you can see here on this drawing these V-groove geometries. The etch depth of silicon depends on the opening. So when you have a large opening, like here, you can get a silicon membrane. Yeah. And the angle between 100 and 111 planes is 54.7 degrees. So this anisotropic wet etching can be used to do micromachining of bulk silicon. And on this picture, you can see an example of this is a tip for atomic force microscope. I don't know if it's clear, but we can see the different sides corresponding to the crystal orientation of silicon. When high resolution is needed, and if you have high density of structures, reactive ion etching is more suitable to etch material. So and reactive ion etching is one technique used in plasma etching. So the reaction between a solid and gaseous etchant results in volatile products. There are two components in reactive ion etching, the chemical and the physical ones. The chemical etching is responsible for isotropic etching of material. So you can see the typical curve profile when material is etched isotropically. And the physical etching is due to ion bombardment of the sample. And this ion bombardment make the side walls of trenches vertical. And this is what we want. We want high resolution, and this is possible with ion bombardment. Okay, so thanks to reactive ion etching, you can get high resolution, and you can see a picture here of holes, arrays of holes with vertical sidewalls. But the main disadvantage of plasma etching is that this is a single wafer processing. So only one wafer can be processed at one time. So on this slide, I summarize the microfabrication techniques in 6 categories. The techniques, the processes in red color are not discussed in this presentation, okay? But for example, here the first one, substrate preparation. So we need to clean, and cleanliness is very important for application when you want to fabricate transistors or for epitaxy. Epitaxy cleanliness is very important because you need, if you have any defects, it will affect your growing layers. So as I told you in this presentation, we can add materials to add more functionalities on the substrate. So we have different techniques: PVD, CVD, epitaxy, electroplating, spin and spray coating. We can pattern, define patterns on the substrate with photolithography and e-beam lithography, but we have also direct laser writing. So this technique is used to write photomask. Okay, and you can write directly on the wafer if you want also. David talked about soft lithography and nano imprint. We can remove material after patterning with etching, so wet and dry etching. We can modify the properties of the material. Doping and ion activation is widely used in fabrication of transistors to adjust the conductivity of contacts or channels. And these steps are used and repeated as necessary to fabricate your micro nanostructures. To give you an idea, I think the last microprocessors from Intel requires over 30 patterning steps. So very huge, 30 patterning steps. And in your case, the mold you will fabricate is only 9 steps in total.
How many steps in total for Intel?
I don't know. I know it's patterning, it's 30, but I would say more than 100. Yes?
In Tal's case, there's many different substances being put on, right?
Sorry, can you repeat?
There's many different substances being layered.
Yeah.
But do all these approaches, can you layer multiple substances using all of these approaches?
For sure, yes, it's very hard to compare semiconductor industry and a lab, research lab. In semiconductor industry, you can use all the material you want. For example, metals. You have to be very careful with metal because metal is very poisonous for silicon. You can create defects, and the transistor cannot work properly. Okay, and I know that, for example, DALSA, when they want to use a new product, they analyze this product. And if it is not compatible to Cleanroom, they don't use it. In our case, we are more flexible. So we use gold, for example. Gold, you never see gold in Intel. Okay, gold is only used for interconnection when the device is done. And you have also temperature problem. So with deposition, sometimes you need high temperature. But if you use a metal which made like chromium, let's say chromium, I think, or aluminum. Aluminum was used a lot at the beginning of microelectronics. But the problem with aluminum is that the temperature, the melted point is 400 degrees, I think. And when you want to use CVD at 600 degrees, you cannot use this technique. So for sure, I would say in industry they are not flexible like us. In here I think we can do what we want. Okay. So when your device is when the fabrication is done, sometimes you need to connect this device to the outside world. So you need to do packaging. So this is why after microfabrication, packaging may be needed for protection from a connection to the outside world. So we have some techniques. So we have wafer dicing. We can dice the wafer to get chips or dies. We can do wire bonding, and we can also do characterization and test, electrical test. So let's see now the example of SU8 master for PDMS molding. So the SU8 resist has been specifically developed for application when high aspect ratio structures are needed. Okay, and this is possible to the low optical absorption of SU8. So when you have a project what you should think about prefabrication is the process flow. So you need to know the techniques, you need to know the tools available in the fab, and you need to know the specification and limitation of these tools. After, you have to design the layout with your patterns and the dimensions. And sometimes the dimensions are determined by simulations. So in the case of SU8 master, what you need, so in the material, it's you need a silicon wafer to provide a mechanical support. You need the SU8 epoxy resist. You need the SU8 developer. You need IPA, isopropylic alcohol, to rinse the wafer after development. You need dilute HF, hydrofluoric acid, or buffered oxide etchant to remove the native oxide prior SU8 spin coating. And DI water, deionized water. In the equipment, so you will use weight benches, spin coater, hot plate to cure the resist, oven also, a photomask and a UV mask aligner, a plasma chamber, I will come back later for this one, and optical microscope and profiler to characterize your structures. So let's see now the process flow of the SU8 to fabricate SU8 master. So as I told you, there are 9 main steps. The first one consists in removing the native oxide with the hydrofluoric acid or the buffered oxide etchant. So why? So it's very important to get to remove this native oxide. Otherwise, the SU8 resist will not stick very well on the wafer. Okay. Then, you have to remove the moisture from the substrate surface. If you have moisture, it can affect also the photolithography process. So you can use the oven or hot plate at 150 degrees for 5 minutes. SU8 spin coating is the third step. You have to bake the resist after to evaporate the solvent from the resist. Step 5, you have to define the patterns on the substrates. Step 6, post-exposure bake. So the post-exposure bake is required to polymerize the SU8 layer before development. So when you polymerize the SU8, this area, polymerized area, will not be removed during development. If you forget to do this post-exposure bake, your wafer will be washed away. And you have to start over. Development. So at this point, cracks can appear in the SU8 layer. This is a well-known problem, and this is due to the release of internal stress in SU8. So to remove these cracks, hard bake is needed, and our bake is done at 150 degrees for 5 minutes. It's above the glass transition temperature of SU8. So you will make it flow, and cracks should disappear. And finally, step 9, plasma treatment. So for today, you will not use plasma treatment, but if you want to use the SU8 master for several times, it's better to do plasma treatment to deposit the fluoropolymer film on the SU8 master, and this can help to peel off the PDMS replica. So can you tell me which steps correspond to the photolithography process? Three to 5. Sorry? 1 to 9. No. Sorry?
3 to 5.
3 to 5. It's 3 to 7. Because, so here, right, so SU8 spin coating, the photolithography process starts here, but you have development.
They are not readable.
Sorry?
They are not readable. The ones are small.
They're small? Oh, sorry. I will make it bigger next time. But so from step 3 to 7, step 3 to 7 correspond to photolithography process. And between step 8 and 9, you can use tools to characterize your structure. So you can do metrology. You can use optical microscope and a profiler to verify the dimensions. Sorry, yes?
After removing native oxide, how do you prevent this oxide to reappear?
Good question. You have to be fast. If you, let's say that one day, today, you remove the native oxide, you wait tomorrow, you have to redo the native oxide etching. It's a very slow process because silicon is known to create, any semiconductor materials can have a native oxide layer. And silicon is due to moisture in the air. So I think the maximum is 3 nanometer, but this 3 nanometer can affect a lot of things in semiconductor industry, like adhesion of photoresist and also electrical properties. So when you remove it, after you have to continue your process, don't wait. And the way, what I do is dehydration can help also to remove, when you remove moisture from the wafer, it helps. But that's why also you have to do it in a controlled environment, in cleanrooms. If you do it in a standard room, for sure your humidity in cleanroom is controlled is about 40%. In this room, maybe, I don't know, it's maybe 60, 70. At home, it can be high also. So for sure, it depends on the humidity level in the room. And sometimes also in semiconductor industry, the wafers after wet etching, after native oxide etching, they are kept in control in a small box, and the atmosphere in this box is controlled also, for no moisture. Yeah, and I would. There are 3 critical steps in this process flow. Step 3, spin coating. So SU8, you will see SU8 is very viscous, and air bubble can be trapped inside the layer and make defects on the SU8 master. Step 4 and 6 are very critical because of thermal stress. If you don't use the right temperature and the right time, you can have delamination problem of the resist. And this is the case, I will show you, this is the case for this wafer. You will see, after the first PDMS replica, the SU8 layer came out. And there was a delamination, you will see on this wafer. So now let's talk about our facility, the McGill nanotools microfab. So here is a floor map of our facilities, and the McGill nanotools microfab can be divided in 3 areas. So first, the going room, where the user has to be dressed to enter in the clean room. Okay, and the second room is the photolithography room with a class 100. So in this room, you will work in this room to make your SU8 master. And you can see that the light is completely yellow. Can you tell me why we use yellow light?
Don't want UV lights.
Yeah, we want to block UV lights. Because the white light, the standard white light here from ceiling, have a small range of UV. Okay? And also UV from the sun, you will see that we have windows with a yellow screen to block UV. So different sources of UV, and we don't want to expose the wafer completely with UV, the small UV emission from white light. So that's why the light is completely yellow. And the last room is used for deposition and etching, and it's a class 1000. Last year, at the end of last year, we received more than $10 million to buy new equipment and to do renovation. And you can see here especially this room will be converted in a new clean room to install new equipment. So the McGill nanotools microfab is 6-inch wafer compatible MEMS fab. We have standard and specialized semiconductor manufacturing equipment. Here is a list of our process capabilities. So we can do thermal oxidation, we can evaporate metals, e-beam evaporation of metals. We have chemical vapor deposition of silicon and its compounds. We have tools for photolithography. We have a scanning electron microscope that can be used for e-beam lithography. We can do wet etching of silicons, metals, resists. We have plasma etching tools, and we can do also packaging for wafer bonding, dicing, and wire bonding. We have also tools for characterization. So of course, optical microscope to look at your structures, a scanning electron microscope. So this microscope is the same as for e-beam lithography. In fact, it's a converted scanning electron microscope. We can do imaging and we can do e-beam lithography. We can use profilometry and to measure the height and the topography of your structures. We have spectroscopic ellipsometry and reflectometry to measure the thickness of thin films. And we can do electrical measurements. Here are some examples of realization from the McGill nanotools microfab. On this picture, you can see silicon cantilevers with aluminum nanowires. Here is a better view of these aluminum nanowires. These aluminum nanowires were defined by e-beam lithography and electron beam evaporation of aluminum. This kind of structure can be useful to study the internal friction of metals on silicon. On these pictures, you can see silicon nitride cantilevers made by e-beam lithography and reactive ion etching. And again, these structures can be used to study the mechanical properties. In this case, it's a low-stress silicon nitride layer. In microbiotechnology, as I told you, so the PDMS molding is widely used in David Juncker group, and I think other labs, to make microchannels. And in fact, the first step is to fabricate SU8 master in the clean room. This structure is very interesting. It's a kind of micropipette made in SU8 layer. And you can pick up some biological solution with this pipette. So you will get further details for these structures in the next presentation, I think. And in optoelectronics, 3-5 metals are also widely used in the fab. Here, we have white light-emitting diode made with indium gallium nitride dots grown by epitaxy. And on this picture, I don't know. Do you see these pictures? We can see bright light emitted from this light-emitting diode. Gallium arsenide and aluminium gallium arsenide quantum well photodetectors were fabricated in the fab. So the active area for detection were made by reactive ion etching of this material, and the Choky gates here at these detectors were made by e-beam lithography and electron beam evaporation of metal. So if you have an ID, if you want to use our microfab, it's very easy to get access. So of course, first you need to gather information in literature and with colleagues to see if your project is viable. Draft a process flow, and you can submit me your process flow, and I will be happy to help you and to make some modification if needed. To get access to the clean room, we have a procedure very well explained on our website, and some of the steps are getting WAMIS certificate, because we use a lot of chemicals, gases, dangerous product inside. So you need to get your WAMIS certificate to enter in clean rooms. You need to pass safety quiz, and after you need to know the microfab policies. We have also software to book the tools, and to each time you use a tool, the time is used to for calculation of fees and etc. For more information, you can visit us at www.mcgill.ca/microfab, and you can contact me by phone or by email. I would like just to give you more information about this book. This book is called Introduction to Microfabrication from Sami Francila. This is a very interesting book, and it's very cheap. It's about $70 from Amazon website. For the McGill students and employees, you can get an electronic version of this book from the McGill library website. So thank you for your attention, and I think I have time. I don't know if I have time for. I have a small video of about 10 minutes. No, we don't have time. We have time?
Yeah, sure.
Okay. I have a small video of 10 minutes from TSMC. So TSMC is a Taiwan semiconductor manufacturing company, which is the world's largest dedicated independent foundry. Thanks to this video, you will see how advanced clean rooms are in semiconductor industry. I hope it will. Ah, no, it doesn't work. No media. No. Yeah.
Okay, so while they're setting up our speaker.
Do you have any question?
Can you give us an idea of how much it would cost to do a very basic project, just a ballpark figure? So,
okay, so the fees to use a tool is $50 per hour. Okay. After it depends on the tool. For web benches, there is a cap, only 1 hour. After 1 hour, it's $50. Okay. There is also a soft cap of 25% when the cost is above $2,000 per month, and when you need the help of staff member of the fab, you have to add $60 per hour. So for a basic project, I would say for SU8 Master, for example, SU8 Master, it's I think it's $500.
So $500 you would get an SVA master.
Yeah, maybe less. But to compare in industry, a wall wafer, in industry now you can find 12 inches wafers. And this with a blank wafer is about more than $1,000. And when it's processed, it can be the price of a car, luxurious car, $50,000. So the industry, semiconductor industry, is very expensive. And we talk about billions of dollars in the world. It's okay. So enjoy the video, and you can ask me questions after this video. Yes, it increase.
I don't know if I can.
No.
There's a plug right there. Oh.
Yeah. Thank you. Thank you.
Alright, let me turn this down.
TSMC pioneered the dedicated semiconductor foundry business model and leads the foundry segment with its trinity of strengths: technology leadership, manufacturing excellence, and customer partnership. TSMC's fabrication facilities, or fabs, feature the most advanced manufacturing equipment. Here, TSMC researches and applies a wide variety of process technologies to manufacture high-quality integrated circuits for customers. Now, let's look inside the fabs at TSMC to learn about the IC manufacturing process. The fab is a giant clean room equipped with many types of air filters to keep the manufacturing environment free from contamination. Air from the outside must pass through many types of filters to eliminate all kinds of particles in order to maintain air quality of the clean room. In addition, the temperature, humidity, electrostatic discharge, pressure, magnetic fields, and vibrations in the clean room must also be controlled. Pure water, as well as special liquids and gases required for the manufacturing of integrated circuits, are supplied directly to manufacturing equipment through pipelines running throughout the clean room. Before entering the clean room, personnel must wear clean room garments, shoes, gloves, and face masks to ensure cleanliness. After changing clothes, personnel enter the air wash room to completely remove dust and particles from their bodies, preventing suspended particles from entering the fab. An integrated circuit, or IC, is a system of electronic components and circuits miniaturized onto a silicon chip 1 centimeter square or smaller. An integrated circuit can process a large number of electronic signals and perform many complex functions. If we look at a chip under a microscope, we can see that the apparently smooth surface is actually stacked with many components of different heights and shapes. How are these components fabricated? Let's start with the raw materials used to make the IC. Silicon wafers are a type of semiconductor material and the basic raw material used in the manufacturing of ICs. By doping the wafer with elements such as arsenic, phosphorus, and boron, the conductivity and characteristics of the wafer are changed. To make silicon wafers that meet the requirements for flatness and uniformity needed to make ICs, raw polycrystalline silicon material is first heated to a high temperature. By adjusting speed and temperature, a cylindrical ingot of crystalline silicon is pulled out. The outer surface of the silicon ingot is then ground to a uniform diameter and sliced into thin silicon wafers. The edge and surface of the silicon wafers are ground and polished. We can now use this silicon wafer to begin manufacturing integrated circuits. IC design engineers first use computer-aided design systems to lay out the patterns for each circuit of the IC. By using electron beams or lasers, these patterns are then transferred to photomasks. The number of photomasks required for an integrated circuit product usually depends on the complexity of the design and the process technologies. Generally, it requires at least 20 to 30 layers of photomasks, and the alignment between each layer must be very accurate. The fab for manufacturing ICs is divided into several major areas. Each area has a unique function.
In the diffusion area,
the silicon wafers are sent into an oven tube for thin film growth at high temperatures. The silicon wafer stays in this environment, where temperature and gas flow rate are accurately controlled for a period of time, and the surface reacts with the high temperatures and forms an insulating silicon compound film. Ion implantation is a process used to implant charged ions into a specific region of the silicon wafer. Conductivity is changed by controlling the concentration and depth of the ions. In the chemical vapor deposition, CVD area, chemical reactions occur in the reaction chamber, and the reactive chemical vapors form a solid-state reactant, which is deposited on the chip surface as a thin film. The wafer is now covered in a thin film and sent to the photolithography area for transfer of circuit patterns. A thin layer of photoresist, a photosensitive liquid, is uniformly coated on the wafer surface. The photomask is then placed over the wafer. Light is exposed onto the wafer through the photomask, creating a pattern of exposed and unexposed areas based on the pattern of the photomask. Unexposed areas remain covered with photoresist. After photolithography processing, the silicon wafer will be sent into the etching area to etch out the exposed regions, that is, the regions uncovered by the photoresist. The remaining pattern is the area needed for the circuits. Once the wafer surface is covered with several thousand to several million electronic components, the components are connected with metal conducting wires so that they can perform their designated functions. Here, the surface-etched wafer is sputter-coated with a thin layer of metal film, processed with photolithography, and etched to remove the unnecessary parts and leave the metal wires connecting each electronic element. The chemical-mechanical polishing area uses mechanical principles and chemical reactions to effectively remove materials on the silicon wafer and make it flat in preparation for later thin film deposition. These complicated and precise processes are repeatedly performed in the fab to complete the manufacture of ICs. Each silicon wafer is made up of hundreds or even thousands of chips. Finally, these chips must pass the acceptance test. After passing basic inspection, the chips are then diced, packaged, and tested according to the purpose of each integrated circuit. Throughout the entire manufacturing cycle, the silicon wafers must be transported back and forth between the different manufacturing areas and manufacturing tools. In a conventional 8-inch fab, the operator usually uses a cart to transport the silicon wafers manually. In recent years, technological progress in the semiconductor industry has increased wafer size to 12 inches from 8 inches. This allows manufacturers to get more chips from a single silicon wafer and reduces the unit cost of IC manufacturing. The weight of a 12-inch wafer is twice that of an 8-inch silicon wafer, and the weight of 12-inch wafers together with the carrier tool are too heavy to transport manually. As a result, they are carried by automatic material handling systems. TSMC leads the foundry segment in introducing automatic material transport systems and automatic real-time dispatch systems in its 12-inch fabs. Everything from wafer transportation to manufacturing is controlled by an automated production system, improving the efficiency of the fab through automation. This was an introduction to TSMC's fabs and manufacturing process. Thank you for watching this video.
Okay, so you can see it's very advanced microfab. You won't even see that in the basement during the fabrication, but it can give you an idea. Okay, so of course, in our fab, in microfab in university, we are more flexible. We can use a lot of material, so it's not a problem. In TSMC, Intel, or AMD, any large foundries, it will be more difficult to ask them to do PDMS molding or to use gold. So do you have any question about this video or about my presentation?
The feature that you showed from Barca,
Yeah.
how many steps maybe?
I don't know, but what I know is that this CCD were made in '95, and you need oxidation step, you need to doping, ion implantation, you need photolithography. I don't know, maybe 30 steps. I really don't know for CCD. But I think that it's a lot of steps. Yeah. Okay, thank you for your attention.